Great. So I'm going to record my lectures with that camera, as I said. Luckily, we have a small enough board that you can pretty much pick up everything on the camera. I'll post them on YouTube at the end of classes if I remember, and post the links on Canvas. So today I want to talk a little bit about what I have up here, the language of physical chemistry. And our language is a little different than other chemists. Actually, it's all chemists share a language, and we pull from the language of other chemistry fields, but there's a certain emphasis that we place on certain types of communication. And I think it's important that we go through them a little bit because, one, I'm a bit of a stickler for some of these things, and also I think it's important to have good skills, especially with quantitative information. So this is a numeric. In some ways, this is a quantitative class. Right? We're going to predict things. We're going to calculate things. And so it's really important for us to be able to understand how to communicate numbers. And also we're going to talk about not only just numbers, but also units of measure. Right? When we talk about, say for instance, we'll talk about units, right? And units are important because I could say the number 3 to you. I have 3 of something, but you have no idea what that means. But if I say 3 meters, you know it's a length, right? Or 3 Kelvin is a temperature. Right, so numbers have 2 elements in chemistry, or in all of science, which is the number itself, the value, which has no intrinsic meaning whatsoever, and the unit, which defines the meaning. So I'm going to kind of have some kind of really generic notation about this, and this will be kind of ridiculous, but I want to talk a little bit about what we call physical quantities. We're going to be measuring a lot of physical quantities in this class, hence the name physical chemistry. Right, and a physical quantity has 2 components. Right, so let's say we have a quantity Q that we measure. Maybe we go in lab. And Q will have 2 components. And I'm going to use kind of weird notation for this. One is going to be with the squiggly, just to demarcate it, and another section, which is Q, in brackets. And so we have a quantity that we measure. This is the numerical value of it, right? The number itself. And the other one in the brackets, the square brackets, is the unit. Okay, and so by themselves they have no intrinsic meaning, but together they make a whole. And it's important to be able to juggle both of these on equal footing, and not to leave one out and leave one in. Of course, there's very rare instances where you're going to report a unit without a value, but there are many instances where you might report a value without a unit. And we should talk a little bit about units because we're going to be doing a lot of units in this class, right? Everything is going to be a measurable quantity, and every measurable quantity has a unit associated with it. So here's an example. So for instance, if you're driving down I-95 at night, and you look up on the sides of the interstate, and there's those big tall lights, right, that encompass the interstate, and they always have that kind of yellow glow to them, that orange glow. And that comes from a very specific light. And so these lights are what are called sodium lights, sodium discharge lights, which have this characteristic yellow glow. Yellow glow. I'm sure you've seen these on your streets or on the interstate or wherever. The way these work is there's a filament inside just like these, right? These fluorescent lights, they have this long filament, and inside of it is a gas. In the case of a sodium light, there's sodium gas, right? Sodium atoms inside of this filament, and we drive a voltage, electrical voltage through it to excite the sodium gas inside of it, and that excitation exhibits a very distinctive yellow glow. All right, and so imagine that we are new prehistoric visitors to Earth. We've been frozen for 10,000 years, and we show up, and now these people, humans have created these magical lights, and somehow we magically know chemistry as well. This is a really dumb example, but and we want to understand, well, what does this yellow glow come from? We want to measure it, right? How do we quantify this yellow glow? And so what Mr. Caveman does is he pulls out his prism or his diffractometer or some spectrometer, measures the light, and he says, okay, well, let's go look at the wavelength, right? There's our quantity, the wavelength. right? That's the length of the light wave, or of one period of the wave. And he measures it, and he says, okay, he also knows SI units for some reason. And he goes and measures it, and he says, okay, I measure it. And he finds out that it's 5.986 times 10 to the minus 7 meters. Right? Okay, so we can identify that there's two quantities inside of this, there's two components of this quantity. Right? There's the numerical value and the unit. Right? If you reported just this number, without the meters, you would have no idea what he was talking about, because it could be in inches, right? Or it could be in light years, or it could be in something that has nothing to do with length, right? So the unit gives the number meaning, right? Otherwise, this is just a number, right? But then when he goes, and then his friend shows up, and his friend asks, okay, what's the wavelength of this yellow glow? And he doesn't understand a notation, the scientific notation, so that Mr. Caveman says, okay, well, the wavelength is 0.12345658986 meters. Well, this is also a problem. I mean, this is why we do scientific notation, because if you're ever going to transcribe this, it's almost always guaranteed you're going to screw up the number of zeros in this, right? So even though that these two quantities show the same information, one is much more useful to us than the other one, right? This one is just totally like nonsense. And you can imagine that we're going to see numbers that are way even smaller than this, and you're never going to want to put the zeros, right? And so what we can also do, the great thing about units, is that we can convert them as well, right? So another way we could write this instead is 598.6 nanometers, where a nanometer is 10 to the minus 9 meters. Right. And this gives us nice information. This is a nice, easy number we can tell people, right? This is a unit that hopefully people understand. If they don't, they can convert between meters and nanometers, because nano always means 10 to the minus 9. It means a billionth. But every single one of these representations give the same value, right? They give you the same meaning, but they're in slightly different contexts. Right? If you have a calculator that doesn't do scientific notation, you're going to have to give it this. Right? But you're never going to want to tell someone this or report this in your paper, because you have all these zeros. It's just a waste of space and it's confusing. So we have to convert the units, right? So we have the same information being contained here, but the difference is the context. And so it's important to understand that units are flexible, and units can provide context. And we're going to see that time and time again, because you're going to come across quantities that we're going to measure, and we're going to use different units for them. But luckily all the units are interconnected. We can convert between them, but some units are appropriate for some contexts, and some aren't. For instance, nanometers is really good for visible light, because it's on the order of 100 or an order of 1, right? It's an easy number to write down. But maybe we're looking at long radio waves, where the wavelength would be on the order of a meter, and maybe we'll just stick with meter, right? So it's all about context. We're going to come across many different quantities where the units aren't so simple, right? Meters and nanometers, these are all really easy to figure out. It's just factors of 10 between them. But there are all sorts of different customary units that people use that have very distinct contexts. And so sometimes this class can kind of feel like a jumble when it comes to units, because the units that scientists use tend to be contextual. They tend to be something that depends on the situation that you're looking at. Okay, so this must seem trivial, and that's okay. I just want to make sure that we're all on the same page about this, because I want to talk now about units. Right, we'll come back and we'll talk about the number, the numerical part of this term or this quantity. But the units are important, because the units define everything about chemistry, right? It tells us it's how we communicate about values and quantitative values in chemistry. And so it's important for us to understand how units work and how we've set them up. So I'm going to go ahead and erase this. And so we use a system of units. We're going to kind of use a consistent set of units in this class that we will kind of use as our standard. And it's an international standard. In fact, the name of it is the International Standard System of Units. I'm sure most of you know all of these already, are the SI units. Again, SI stands for International System, but in French, so it's flipped. That's why it's not called the IS units, because it's SI is I think the people who do this are in Paris, so the French get the name. And they've defined what we call fundamental units. They have a set of what we call fundamental units. Defines a set of standard fundamental units. There are kind of fundamental quantities that we can measure in the world or in the universe, and we have a set of units to represent each of them. The first fundamental quantity that the SI units measure is time. All right, what's the unit for time? Seconds. All right, so seconds. Right? We often represent time. The unit abbreviation is S or SEC sometimes, but usually it's S. This is the symbol we use. And then sometimes we write time as T. So if it's a variable in an equation, we typically write it as T. Right, does anyone know what the second is defined by? Any ideas? We have to have a reference, right? We have to have some standard to define what a second is. And it's very interesting. And about last year, these scientists came together and decided on a new standard system for the units and how to define them. And the way that we define units is by fixing things and defining the units relative to that. So the second is defined based on a wavelength of light, an emission from a cesium atom, and it's defined as a certain number of periods of that wave. Okay, and in fact, I'll just write it here. 1 second is defined. This isn't all that relevant, but it's kind of interesting, as the time elapsed during 9,192,631,770 cycles of a particular emission of the cesium atom. Okay, so they have in DC, outside DC, in Bethesda, Maryland, and also at the Naval Observatory in Annapolis, they have these clocks that are called cesium fountains, and they're literally just really, really high precision apparatuses that measure this emission of the cesium atom to very, very high precision. Right? And so they're the timekeepers of the world. And so it's defined to be exactly this number. Right? It's just the number that they choose is actually very reasonable because it's proportional to the wavelength or the frequency of the light emitted from the cesium atom, this ridiculous number. But it's fixed. Right? So anyone who can pull up a cesium atom, I don't know why you would ever do this in your garage, create your own garage fountain, measure this, and you know exactly that the frequency of it is this, 9,192,631,770. Right, so it's a nice standard for time. And that's really nice because we can be 10 million light years away, and we can still pull a cesium atom out and be able to count. Right, so that's the whole point of this. The second of the fundamental units, so another simple one, is length. Anyone know what the unit for length is?
Meter.
What's that?
Meter.
Yeah, meters. M. And a meter is defined, interestingly, the amount of distance traveled by a photon, right, a light particle, emitted from the cesium atom during 1 over 299,792,458 of a second. So here's the really cool thing about this, is that these are bootstrapped, right? We fixed time to be this exact quantity, right? This exact period. 1 second is exactly this many cycles of the cesium atom. And length is defined as a specific fraction of a second, or a specific fraction of, a specific fraction of time that's fixed by this, that a photon travels at the speed of light, right? So we wouldn't be able to measure length without measuring time. So they're interconnected to each other, right? They all build off of each other, and this is one of the big kind of, before the last couple of years, the SI units had all these different standards. They were all crazy, and now they all kind of come together in this like, what's the word I'm looking for? Kind of like in a symbiotic relationship, right? They all kind of reinforce each other. The third one is mass. And what's the SI unit for mass? Kilograms, not grams. Remember that, kg. Well, there are going to be a lot of quantities when we talk about mass, and almost always we're going to talk about kilograms because that is the metric unit of mass. Grams, again, are sometimes more convenient because, like, for instance, the masses of atoms are on the order of 1 gram per mole to 100 grams per mole, give or take. So kilograms is kind of an unfortunate unit for chemistry, but everything's relative to a kilogram. It used to be that a kilogram was standardized because they had this mass of metal. I can't remember what it's made out of, but it's this cylinder of metal that they store in a very, very, very clean environment under vacuum that they define as a kilogram. So if the world collapses and civilization ends and we need to figure out what a kilogram is, you would pull that mass out and weigh it, and that's a kilogram. But what they realized is that even though it's under that really clean environment, that the mass drifts over the course of decades. And so every year, they realized that the kilogram, the standard kilogram, the kilogram that you pulled out in France or in America, was gaining about 10 micrograms every year. And they just couldn't fix it. So every year they'd have to spend all this money to clean it and to recalibrate it and to fix the environment and stuff. But due to oxidation and due to dust sneaking in and other types of things, gas absorbing to the surface of the kilogram, they decided to get rid of it. So now the kilogram is no longer defined by any mass. In fact, what it's defined by is that a kilogram is defined such that the mass of the carbon-12 atom, right, carbon-12 isotope, is exactly 12.0 grams per mole. Right, so they use carbon-12 now. Right? So what they can do is now you can measure the mass or the size of a single atom, and so now they can define it relative to something without having this mass, right? So it's defined to carbon now. So carbon is the keeper of weight, if you will. So very interesting, and this was a really big deal. And it's really saved a lot of complications. And there's also really nice advantages that will come from this that we'll talk about later as well. The last one I want to talk about, there are a few more, and I'll mention them briefly, but there's one more that we really care about, and that's temperature. And what's the SI unit for temperature? No, not Celsius. Kelvin. Now, let me ask you guys, why would Kelvin be a more appropriate standard measure of temperature than Celsius? Yeah, go ahead.
Isn't Kelvin related to absolute zero?
That's exactly right. So 0 Kelvin is absolute zero. Right? So it's defined versus the lowest possible temperature it's actually, as we'll learn, it's physically impossible to reach 0 Kelvin. But it is literally the lowest possible energy or temperature that you can reach. So it's a very natural absolute scale. As a comparison, what is 0 Celsius defined by? What's that?
Freezing point of water.
Yeah, freezing point of water. Well, it's technically what's called the triple point, but yeah, the freezing point as well of water. So at a specific pressure, we'll learn about this more once we talk about phase changes and stuff. The triple point is where gas, liquid, and solid water coexist simultaneously, but it's also roughly the melting point of water. And so by using Celsius, you're doing everything relative to water, right? Which turns out to not be that particularly useful, because if you need to recalibrate, you're going to have some water. You're going to have to measure the pressure, and that's going to need to be accurate. You need to measure the temperature accurately. You have to make sure the water is pure, because if you have a little bit of salt in your water, as we'll learn, that changes the boiling point and the melting point of water. So we just get rid of Celsius. Celsius is convenient for chemistry because we do a lot of things at the range of 0 Celsius. But absolute zero is absolute zero. So that's why we stick to Kelvin. You can't go any lower than that. Yeah, so those are our big units, right? So there's only 4. And it turns out that just with these 4, there's one more, sorry. One more. And this one's also important. I always forget about this one because it's a different kind of unit. And it's the amount of substance and what I mean by that is that it's a counting unit, right? We count, so for instance, it's a unit to count anything. Does anyone know what it is? We use it in chemistry all the time. The mole. The mole is a unit, is an SI unit now. It didn't used to be, it is now. So those are our 5 units, right? So everyone knows what a mole is, and a mole is defined such that, I don't remember the exact number off the top of my head. It's defined such that 1 mole of an object is exactly Avogadro's number. So they fixed Avogadro's number, 6.02 times 10 to the 23, to a fixed value. It never changes anymore. And 1 mole is defined as that many particles, right? So a mole of anything. These 5 units make up everything that we're ever going to do in this class. But the cool thing about units is you can combine them and mix and match them. There are 2 other units that we won't use very much in this class, but they are in the SI system. One is electric current. Does anyone know what the electric current unit is?
Amps.
Yeah, amperes. The way that they define an ampere is very interesting. It's a little beyond this conversation, but it's very cool how they define something with respect to current. They use superconductors to measure current. And the other one is what's called luminous intensity, or brightness. Does anyone know what the unit for luminous intensity is? It's to measure the brightness of a light.
Lumens.
Yeah. So it's not lumens. That's a radiance. I think it's a slightly different unit. It's called candelas. And the candela tip was originally invented as a reference, and it literally was a reference candle. They made like back in the old days, they had a candle made out of a specific type of wax that they kept in a specific environment, and the brightness of that was 1 candela, which is a really stupid way of doing things, which they got rid of that very quickly. I don't know how they determine candelas anymore. I'm not a guy who does lights, so I don't remember how they do it. But we won't use either of those in this class. Maybe current will come up when we talk about electrochemistry, but probably not. Okay, so these 5 units are the ones that define everything, right? We're going to measure everything with respect to these 5 units. But there are quantities that are more complicated than mass or length or time or temperature. So we're going to also have to look at those, what we call derived units, which are combinations of these units. Any questions so far? Okay. Yes, go ahead.
What about liters?
Well, so that's a derived unit. Great question. Let me ask the class. What is, in terms of these 5 units, what is a liter defined as? Let me ask a different question. What does a liter measure?
Volume.
Volume. Does anyone know what the units of volume are? Just generally?
Cubic meters.
Yeah, cubic meters, right? So it's length cubed, right? So we'll talk about that in just a second. We'll talk about volume and we'll talk about pressure too. Those are derived units, right? They're combinations or multiplicative combinations of all the different units, right? Surface area is meters squared. Volume is meters squared. And then we'll talk about pressure, which is a little more complicated. Any other questions? Okay. Okay, so this is kind of generic, but I just wanted to emphasize it because we'll talk about units a lot. So let's look at derived units now. So these are the fundamentals. Let me just write them down over here. So the fundamental units are meters, seconds, Kelvin, and moles, and kilograms. I'll often write meters, symbols like algebraic symbols for meters, I'll often write as X or L. Seconds, of course, is T. Kelvin is big T. Moles is N, usually, N for moles. And kilograms is M, is little m, usually. Right, those are the symbols. So if you see any of those symbols in my equations as they come up, that's usually what these represent. Okay, so let's look at derived units now. So Megan already brought up volume, which is a good one. All right, we'll talk about volume plenty. It's meters cubed or length cubed. Right, it's if you have a box, right? The volume of the box is the width times the length times the height or the depth of the box, right? And so each of those have units of meters, so it's meters cubed. Another interest, so let's do something a little different. What about energy? Right, we talked about energy last class. What's the unit for energy? Joules. Joules are also a derived unit. And it might be interesting why, or I'll just write it out, joules, or J. In fact, we'll have multiple different types of customary units for energy in this class, but we'll stick with joules for now, because it is the SI unit for energy. It's not a fundamental unit, but these are derived units. Let me just write that again. And let's talk a little bit about how we can define joules in terms of the fundamental units. Okay, and there, again, as we'll learn, there's many different types of energy. And there are different types of units that represent the different types of energy. But we'll use the Physics 101 definition for energy, which is what's called work, which is the energy consumed to, let's just say, move a massive object by a force. Okay, so we'll come back to work because, as we'll learn, chemicals can do work, right? If you have a car, the combustion in your car does work. It pushes a piston up and down. All right, and so, but this is a certain type of energy called work. And of course, the physicist, the way that the physicist always writes about work is that there's a person applying a force, which I call F, against an object with mass m, some distance x, delta x. Right? We want to apply a force and push the object x. And work, the total work of doing this is the force times the change in distance. Okay, so the further you push it, the more energy you consume, or the harder you push it, the more energy you consume, right? Either the force goes up or the distance goes up, the displacement, if you will. All right, so let's work out the units for this. Well, let's do the easy one. What's the distance of displacement? The distance we move the box. Meters. Right? So we're already there. But now we have to calculate the units of force. Does anyone remember from physics what the term for the units of force are? Newtons. But newtons, let me write that down, is also a derived unit. So we have to break it down a little more. And of course we can use Newton's second law, which is F equals m times a, mass times acceleration. Okay, so we can break that down now. The units of mass are kilograms. All right, what are the units for acceleration? Man, you guys are good. All right, meters per second squared. All right, so we can put these all together. So we have kilograms, meters per second squared. That's a Newton. This is a Newton. Times length, meters. Kilograms per meter squared, kilogram meter squared per second squared. That's a joule. All right, so that's how we represent a joule in terms of the units of SI units, fundamental SI units. You can see a problem, though, is that when I tell you that the energy exerted by pushing this box is 1 joule, you're like, okay, I kind of get a sense of what that is, some amount of energy. Maybe you think about how many calories your breakfast was and you can compare, right, or something like that. It's a very customary unit. It's very nice. We have nice comparisons. But if I told you I exerted 10 kilogram meter squared per second squared, you just your eyes glaze over, right? And that's important, is that these derived units, we often, things that are very customary that we use a lot, we're going to rename. And we're not going to really worry so much about the SI units that make it up, because we'll just use the customary derived unit, because that makes a lot more sense to us. So I'll just write this. This is kilograms per meter per second squared. Now, there might be a situation that we want to convert from joules to another unit. And in that case, we may have to break our unit down here with dimensional analysis and convert to a more appropriate unit. And in fact, there's a problem on the homework, on homework 1, that talks a little bit about this conversion. Any questions so far? Okay, yeah, that's pretty straightforward. So in the notes for this class, there are a bunch of different derived units that are useful in physical chemistry, some more useful than others. Things like Celsius is a derived unit technically, energy, power, charge, frequency, force, as we saw here, volume, area, and so on and so forth, right? But they can all be represented in terms of these fundamental units. And so there's a really nice chart that I posted in the notes with all the actual representations of each derived unit in terms of their fundamental units. Okay. Let's look at pressure, because we're going to talk about pressure a lot in this class. And pressure is the last one, I think the last derived unit we need to really care about right now. So a really easy way to define pressure is, let's see if I can draw this. I'm not a particularly good artist. Actually, that's not too bad. All right, so imagine that this is a tile on the floor. All right, so I'll just draw some. I'm not going to draw anything out. It's a tile on the floor. And, I'm sorry?
You're looking for force over area?
Yes, that's right. Yeah, you got it. Right, so pressure, force over area. Right, Newton meters, right, exactly. So this is Newton per meter squared, which is, let's see, kilogram meter per second squared over meter squared, which is kilograms per meter per second squared, right? Which is a totally useless unit, right? And the way to think of pressure again is this: is you have for instance, a bowling ball sitting on this tile that has a mass m, and it's exerting a force against the tile of gravity, right? Which is F equals the mass of which is the mass of the ball times 9.81 meters per second squared, which is the mass of the gravitational or acceleration, over the surface where it touches. Right, so here's the surface area where the ball touches. The ball touches, and so the pressure is that force pressing down on the surface area where the ball touches. Okay, so the units for pressure, the derived units for pressure, does anyone know what they are? Pascals. We're not going to use pascals very much. And let me tell you why we're not going to use pascals much. For instance, let's talk about the most customary unit for pressure, which is atmospheric pressure. All right, so a customary unit for atmospheric pressure is what's called the atmosphere. It's the atmosphere, or ATM. And 1 atmosphere is 101,325 pascals. It's not, well, this is not a particularly useful unit. Right? And so, for chemistry especially, right? We do a lot of chemistry around an atmosphere. And so using pascals are kind of useless sometimes. Pascals are the only time pascals are typically used in chemistry, maybe some exceptions, are at very, very high pressures. So there are these chemists, for instance, really good at physical chemistry experiment is that hydrogen, molecular hydrogen is predicted to turn into a metal at very high pressures. You can make metallic hydrogen. And so there's been a lot of, for like the last 10 or 20 years, these apparatuses that generate extremely high pressures have been, these groups have been trying to make metallic hydrogen. And they're doing these measurements on the order of gigapascals, right? Billions of pascals. And so that is another 3 or 4 orders of magnitude, right? So they're at 1,000 atmospheres or so. Right? And so they often represent things as gigapascals or kilopascals. Some engineers use pascals as well, but we won't typically find pascals in this class. Instead, we'll use atmospheres a lot. Another unit that we're going to use is bar. And a bar is very close to an atmosphere, but it's just 100,000 pascals instead. So we'll use that unit a lot. Another one that we'll use a lot, less common, I like this unit because it's very useful for vacuum work, is a torr. And a torr is a really stupid unit. It's 133.322 pascals. Or, let me see, where is it? Atmosphere, torr. Or 1 atmosphere, I'll just write this here, 1 atmosphere is 760 torr. If you've heard millimeters of mercury before, millimeters of mercury is a torr. It's an old unit named after the physicist who really started studying pressure. He's an Italian physicist. His last name is Torr. I can't remember his first name off the top of my head. And he used, again, mercury. He used a mercury manometer to measure pressure and water and all as well. And so the unit's named after him. And so if you've ever heard the term millimeters of mercury, it's the same as torr. So that's another common unit that's used, but it's not that useful, except if you're used to using torr. Again, often these things are contextual. So we're going to use these a lot, and it's important to know how to convert between them because even the book interconverts between them as well. Some things are in atmosphere, some things are in bar, some things are in torr. There's one other unit that I'm just going to mention, which is a pound per square inch, PSI, which again is what your car tires use, which is a really silly unit, but people use it. So 1 atmosphere is 14.6959 PSI. Right, so we'll never use PSI in this class, but I thought I'd mention it just to have it here because again we use PSI a lot in real life, right? Bicycle and any sort of tires usually measured in PSI in America. It's an American imperial unit. So don't get scared. Again, there are going to be many different customary units for pressure. in the book and also around the world. And so these are all kind of how they're related. So this is pressure in some ways is one of the units where we will only occasionally use the SI unit for pascals. So we'll use these more appropriate, contextually appropriate units like bar and atmosphere. Any questions? Okay, so I'm done with units for now. Again, we'll come back to this. I just want to make sure that we're all on the same page about units. And I want to switch now. We've talked now about the unit part of a quantity, and let's talk about the numerical part of the quantity. So this is a class where significant digits are important. And so I just want to review the significant digits really quick. I know that the way that they're dealt with in chemistry, your chemistry studies can be kind of oscillatory. Right? Sometimes they matter and sometimes they don't. They matter in this class. So what I'm going to do is I'm going to write down 3 simple rules. And then we'll do some exercises. Significant digits only have 3 rules. One is that non-zero digits are always significant. The second rule was that any zeros between significant digits are significant. So any zeros between 2 sig figs are significant. And a final zero, final or trailing zeros in the decimal part are significant. Okay, very simple. So let's try some examples. I'm going to write numbers down and let's see how many significant digits it has. 100. 1. All right. The interesting thing about significant digits, even though it seems kind of like a silly thing, significant digits automatically inside of them encode some sort of uncertainty. Right? Since this is the only significant digit, if you count for rounding, then what that means is that this number is 100 plus or minus 50. Right? Because if it's 50, you're going to round up to 100, that one significant digit. And if it's 150 or 149, you're going to round down. Right? So by just knowing that it has one significant digit, you can make an approximation for how uncertain the number is. Now let's take that same number. I'm going to add a period to the end. How many significant digits is that? 3. Right, the significant digit, all 3 are significant. Right? And this means something completely different. Right? This means 100 plus or minus 1. Actually, it means 0.5. Sorry. Right, so it's got a factor of 100 more precision because it's got 2 extra decimals of precision. Yeah, so so this is very helpful. And let's try a couple more. What about this one? Let's do 100.1230. How many significant digits is this? 7. Right, this one is significant. The whole thing is significant. That's right. All right, you guys got the gist. Now I've got a fun one for you. So the speed of light, the constant term for the speed of light is c, is defined as 299,792,458 meters per second. Right, that's how it's defined exactly. How many significant digits does it have? How many, sorry?
9.
Actually, I kind of like that answer. I was going to go for infinite, but that's also an interesting way of looking at it. Exact numbers things that are defined exactly, are infinitely significant. I wouldn't necessarily say 0 significant digits because that means that it can be any value, but maybe infinite significant digits. So when you're doing significant digit calculations, for instance, and if you have a constant like this that's placed inside of it, then you don't have to account for it. It basically doesn't count for when you're doing your significant digit evaluation because it has infinite significant digits. All right? So fixed constants always have significant digits. For instance, if you were measuring something like, if you had a model where you're measuring y, that's not a very nice looking y, measuring y with an apparatus that has an input x, where the apparatus multiplies it by 2, this 2 is defined exactly. Right? This 2 has infinite significant digits as well. Right, so any sort of static number, fixed number, always has significant digits if it's defined exactly. Okay, and so the one other rule that I want to add is that when you start doing quantities, you start doing valuations with multiple numbers. So I'll add a different rule. And let me make sure I have this defined properly. The least significant number in a calculation defines the number of significant digits in the answer. So if you're multiplying a bunch of numbers that you've measured, a bunch of quantities that you've measured, bless you, the output of that formula or that calculation should have the same number of significant digits as the least significant number in the calculation. Let me give you an example. Let's say, for instance, let's do a nice example. Let's imagine now we go into the lab and we're going to measure something. So let's measure concentration of some species. What's your favorite molecule?
Water.
Water. All right, so the concentration of water and then the rate constant of some reaction. Okay, and if we remember, rate. And we'll do this in per seconds. All right, we know that the rate is equal to some constant times the concentration of water, just from kinetics. Let's just say it looks like it's a linear relationship. And so you go measure your concentrations, and again, what's the unit for concentration? Moles per liter. Right, that's our moles per, actually maybe we should be more specific. Let's just call it moles per decimeters cubed, right? That's a liter. And the best you can do is measure two significant digits, but in your rate you can measure, your rate's much more accurate. Maybe you can measure something like 698. 1337. This is not to this relationship. We'll just put a constant here. 4200. Something over 9,000. And 11,000. Okay, and we want to measure the rate constant, right? So what we're going to do is we're going to do a statistical relationship between the rate and the concentration to get the constant out, right? We do like an Arrhenius plot, some sort of plot to get the rate out. And you put all these numbers in Excel, right? And you do a line fit, and you get K out. And let's just say K is 420 per second. All right, let's put a bunch of numbers. When you Excel, again, Excel has no knowledge of significant digits. It just puts a number out, and it gives you this number. All right? Now, given the number of significant digits, what should we actually report this as?
420.
Yeah, just 420. And the reason why is because we're limited by the number of significant digits in our concentration. Right, so in fact, this is actually 420 plus or minus 1. Right, so we're always limited by the number of significant digits. Actually, no, it's actually 5. Sorry. 20 plus or minus 5. Right, so that's really important. And I just want to say this just because I'm a stickler about it. Like there's going to be questions where this comes up, both in lab if you're taking the lab component of this course, and in the homework, where you're going to do calculations and calculate. You know, when we do the ideal gas law, you're going to calculate certain quantities. The calculator's going to spit out a bunch of numbers, and if you just write all those numbers down, I'm going to mark it wrong by you're going to lose a point or something like that, right? So I really look for precision. But the rules are very simple, right? Just take the number of significant digits that are on the number that's least significant and just round your number down to that. And then you'll be golden. Any questions about that? Cool. Okay, so I just have one more comment I want to do. One more thing to do before the end of class. We've done significant digits. And this is more useful for the lab component, but I thought I'd bring it up now. And we'll do a little exercise at the end of class here for you. It's about uncertainty. So again, here I've written for the uncertainty for this measured rate. I forgot the units. Don't never forget the units. Plus or minus 5, right? This is the uncertainty in our measurement. Right? And so imagine that you've measured a bunch of different things and you multiply them all together to get a new value. So for instance, let's do this. So an equation that we're going to see time and time again in this class is the ideal gas law. Not only are we going to look at the ideal gas law, but we're going to look at the laws for non-ideal gases. And again, it's PV, pressure times volume equals moles times the gas constant R times T, temperature. So let's imagine now you're in lab, you've got a gas inside of a beaker or some sort of sealed container. You know the volume, you can measure the pressure, you know the temperature, means you can calculate N. So that would be N equals PV over RT. Let me make sure I have my numbers right here. All right, so let's imagine now we go measure the pressure and the volume and so on and so forth. If I can find my piece of paper that actually has these numbers on it. I know I'm close. Here we go. Right? And so we go into the lab and we measure pressure 1.00 plus or minus 0.01 bar. And we got a pretty good measurement of pressure, 3 significant digits worth. We measure volume. Volume's pretty easy to measure accurately. We measure 2.10 liters, plus or minus 0.01 liters. And temperature you can't measure nearly as exactly, but it's roughly 298 plus or minus 1. Actually, let me change that. $300 count. Now, R is a constant and it's a fixed value, so it has infinite significant digits. And I'll just write it here at 0. I'll just show you how ridiculous this number is. So it's 0.083. You don't have to write this down. 144626185324. liter bar Kelvin per mole. That's an exact number. So it's got 17 significant digits. If it weren't exact, I think it's 17. Right, so when we do this calculation, we can just kind of vaguely look at our derived values, and we know what our significant digits on n is going to be. What would it be? Sorry, I didn't hear that. Did I hear something? 1. Why is that?
Because the temperature only has one significant.
Exactly. Temperature only has one significant digit. Now, here's the different question. Now, what if I write this? How many significant digits does T have now? Yeah, it's 2, maybe 3, right? It's probably, it's kind of in between, right? Because this number could be 299 or 301. So that certainly means that these two are significant. But it's not like this number can be such that this number changes, right? Because this would have to be a 5 or a 6 for this to become a 1, second digit. Right, so this has something between 2 or 3 significant digits. And so what uncertainties are, if you can think about the way I like to think about it is significant digits are a estimation of uncertainty. They give you kind of an order of magnitude estimation for your uncertainty. But we should be if we want to be precise, we want to define the uncertainties exactly because they're more precise and they're more of a fine-grained approach to significant digits. All right, so temperature, again, kind of has 2 or even kind of like 2 and 2.8 significant digits on it. It's kind of a weird number, right? So when we do real science, significant digits are nice for quick evaluation. But really we want to use uncertainties because uncertainties tell us exactly what the uncertainty on our derived value is. Okay, and so I just want to define a couple of things and then show you a really nice formula that you can calculate uncertainty for any equation. All right, so imagine that we have a quantity Q. Right, where we write a number, which I'll write like this. Right, from that notation before. It's got units as well. And then we give it an error, right, plus or minus delta Q. Right, this is what we call, this number right here is what we call the absolute error. Okay, so the absolute error on our pressure measurement is 0.01 bar. Absolute error on our volume measurement is 0.01 liters, and so on and so forth. Well, what we find is that absolute error is nice, but it's not a particularly useful measurement of anything. And let me explain why I mean by that. For instance, let's say, again, let's say we measure T to be 300 plus or minus 1, right? And this 1 Kelvin is the uncertainty on our thermometer. Imagine we cool the system down to a really low temperature. Cool down the liquid nitrogen temperature to 77 Kelvin, but it's still plus or minus 1. Which of these are better determined? Which one's more precise?
77.
It's not 77. What did you say?
I said it was the top one.
It is the top one. And let me tell you why. The reason why is, what's the fraction of the error with respect to the value? All right, so let's calculate now the error in the temperature divided by the absolute value of the temperature. So the first one is 1 Kelvin over 300 Kelvin, which is, whatever that number is. It's 0.0033 repeating. And the other one is 1 Kelvin over 77 Kelvin, which is some number larger than that. Does someone have a calculator out of curiosity? Here, I'll just use my phone. 0.013. Oh, I think I missed a zero on this one. 0033. Yeah, that's right. Sorry, that's right. Yeah, so this is this quotient where the error divided by the value is what we call the fractional error. And the fractional error tells you more about how precise your measurement is. We can convert fractional error into percent error by multiplying by 100. So percent error is fractional error times 100%. Right? So if we multiply this by 100%, we bring this over. So this is 0.33% error, repeating. If we put that there, it's 1.3% error, right? So our uncertainty is poorer on our lower measurement than this one, right? And we wouldn't really know that. We would look at these and say, okay, they're roughly the same. But in terms of error, right, the uncertainty of the value, we're at much higher uncertainty in this lower measurement than we are in the upper measurement, right? Because we care about the fractional error. Okay, so it's important to notice that error is also contextual with the quantity. So now what I want to do is just for the last couple minutes is now come up with a way to express the fractional error of a new number, n, for instance. This is the thing that we want to calculate from the uncertainties of the numbers that we've measured. Okay, and there's a really, really nice formula for it. I'm going to go ahead and erase this real quick. So let's go ahead and use this equation here. Well, let's just use a generic one. How about that? So let's imagine we have a quantity Q. We want to measure the uncertainty. And Q has a formula that's like A times B times C over X times Y times Z. Right? Just like PV over RT. Right? So these are some quantities that we can measure. They have errors. Okay? And there's actually a formula for us to calculate the error of Q from the errors the uncertainties of the numbers that we measure. Okay, and that formula is like this. So here's the error divided by the absolute value of the unit or of the quantity. Right, that's the fractional error of Q. Is equal to the square root of the sum of the squares of all the numbers inside the formula of the fractional errors. So it's going to be delta A over A. Right, the fractional error of A plus the fractional error of B. Sorry, that's a little b squared plus the fractional error of C, and so on. And so on. This also works, this equation also works if Q is A plus B plus C, or plus or minus, doesn't really matter, D plus, and so on and so forth. Like, even addition works the same way. Right? You can use this equation for any of them. Right? So whether it's a quotient and a product of numbers, or it's a sum or a difference of numbers, you can end up using the same formula for it. Right? So this gives us a really, really nice formula that we can calculate, we can use for any equation. All right, so let's go do it for our measurement here. Okay, so then that means that the fractional error of moles divided the fractional error of moles, which is delta n over n, is equal to the square root of the error in pressure divided by the value that we measure of pressure squared plus the error in volume divided by volume squared plus t, the fractional error of t divided by t squared. And then we can ignore r because r has infinite value, has infinite precision, right? So the fractional error of r is 0. So we don't have to put it in here, it just goes away. Right? And this gives us a nice formula right here. Right? And you can do this for any equation you want. There are different formula for more complicated functions, but we don't have to worry about that right now. A lot of the things we're going to be doing are products and quotients and sums and differences. So this is the one equation we really need. We can talk more about other ones as we get to it. And so let's go ahead and plug it in. So delta P is 0.01, right? 0.01 delta P divided by the value of pressure, which is 1, 0.00 squared. And then we do it for volume, 0.01 over 2.10 squared. Plus the difference in temperature, 1 over 300. Someone calculate that for me? Yell it out if you get an answer. Got any answers to it?
I got 0.01156. Do you want all of the digits up to come?
No, that's enough. That's good enough. We know roughly how many digits we need because we have roughly 3 significant digits, right? So we're going to be up to about here, right? Okay, so that's the fractional error, right? So that tells us that the error on n, right, we multiply by 100%, is about 1.1%, okay? And so we can get the absolute error by multiplying, so this is the fractional error. And we can get the value of the absolute error by multiplying by n. Right? And so now we just have to do this calculation real quick. And I'll sit here and do it real quick too, because we're running out of time. So now, in order to get the value of n, you just have to do PB over RT with the values that you've measured. So that's going to be 1.00 times 2.1 divided by the gas constant. I'm just going to do 6 times 300. And you can calculate it yourself. But n, the value of n is 0.0842. Right, this is mole. Okay, so the absolute error is going to be this times this. So we take that value and multiply it by the fractional error, 0.01156. I'll write this up here. So n 0.0842 mole. Delta n over n is 0.01156. So that means delta n is 0.000, that's I wrote zeros on top of each other, 3 zeros, 97.
Wait, Jesse, it's close.
Okay. So let's write that out. So let me write that. Now we can put, where am I going to put this? We don't need these numbers anymore, so let's just put it here. Oh, I did need the numbers. Well, that's okay. We know there's 3 significant digits. So the number that we measure is 0.0842 plus or minus 0.000973. Where is the first insignificant digit on our, what's the last significant, based on this error, what's the last significant digit of our calculation? If you notice, it's just slightly more than 3 significant digits, right? Because the error starts, the first uncertain digit is the digit after the 2. Right? And that's exactly what we would have gotten from significant digits. Remember that P, V, and T all had roughly 3 significant digits. So we would expect that N would also have 3 significant digits. But when you do the actual calculation, you get that answer, but you realize it's just slightly, by about 3 parts in 100, more precise than what you would get from the significant digits. Right, so the way we would actually report this, I don't remember what the next digit was. Do you happen to someone happen to have this number still up? The N number?
Yeah.
3, what is it? 8435?
Yeah.
All right, let's stick with that one. Right, so we have, so the first insignificant digit is the 4th digit after the decimal place. So it would be right here. And
235, I guess.
Oh, I'm sorry, say it again.
235.
Right here, 84235? Oh, 84235, thank you. Thank you. Plus of this. So the first insignificant digit is this one right here, which is this one. So we would write this as 0.08423. Actually, we would round this up to 4, plus or minus 0.0009. It's actually 1. All right, we round up and it's 1, so we would get rid of this. All right, you round this up to this digit, that's 001. So that tells us exactly that once you round things up, you have 3 significant digits. All right, so that's why significant digits are so useful, is that it gives you kind of a nice approximation of the uncertainty that you have in your number, but it's not exactly precise, right? We're off by, if once you include all the digits, you're off by about 3 parts in 100, right? And there are measurements in the world where those 3 parts in 100 matter. So often we use this uncertainty relationship so that we can calculate it exactly. But you can see that it correlates exactly with what we would expect from significant digits. There are different types of methods where these numbers definitely do matter, these 3 parts. Okay, any questions about that? Okay, so that's all I have for this kind of like generic kind of opening stuff. On Tuesday, we're going to dive into gases. All right, we're going to come back to the box of atoms, and we're going to stick in that box of atoms for a long time. And things are going to start getting crazy in there. So there's a homework up. It's due, again, the survey's due on Tuesday. If you want to do it, it's optional. There's a problem set on this stuff that we talked about today. It's due next Friday at midnight. And enjoy your Labor Day weekend.